One of the things that brakes need to be sized for is called brake fade, and it is a temporary reduction or even a complete loss of braking force. It's usually caused by a buildup of heat in the brakes. Here's an example. You can see disc brakes look like they're on fire. They're glowing from the heat. It happens actually more often with drum brakes because they're enclosed. It's harder for the heat to get out, but disc brakes are susceptible to it too. The heat itself is clearly caused by the friction between the calipers of the brake and the rotor, in this case, the disc, or between the shoe and the drum. But the loss of braking force is caused because there can be outgassing at the friction material. It's held together with like a resin binder, and when it gets too hot, it can start to produce gases, and that builds up between the caliper and the disc. And so it reduces the coefficient of friction and can reduce your braking force. Also, you can get boiling in the brake lines. Brake fluid is hygroscopic. It means it wants to absorb water. And so if you have had your brake lines, if you've topped it off but left the cap off, and your line isn't sealed, or even just over time, it can absorb water from the air. And that water is more likely to boil at lower temperatures, causing gas in the lines, and it's going to make them feel spongy, and you're not going to get the same force. So how do you prevent that? Well, usually it doesn't happen with just a single use of the brakes, but you do need to size them so that they have enough thermal mass to accept the heat without raising the temperature too much. And you also need to make sure that they can dissipate that heat energy quickly enough. And so we're going to take a look at those thermal considerations of brakes. It applies to clutches too, but brakes are even more susceptible because they end up dissipating more energy. So it's a hot day, it's 100 degrees Fahrenheit, and a truck that has a mass of 6,000 pounds, that's pounds mass by the way, it brakes abruptly from a speed of 68 miles per hour, that's about 100 feet per second. Each of the four brakes has a thermal mass of 10 pounds and a specific heat capacity of 0.1 BTUs per pound mass degree Fahrenheit. So, we are required to find out how hot the brakes get after a single use, and we need to find out whether that's okay. And in order to determine that, we need the following equation. This tells us that the temperature rise is equal to the energy that's dissipated by the brakes divided by the specific heat capacity of the material and the mass of the brakes, or the thermal mass of the brakes. How much material is going to get hot? Now, we're assuming it's all the same material, so it all has the same specific heat capacity. This is a pretty general equation that's true for a lot of situations. We're going to apply it to brakes right now. It's a very simple statement that the temperature rise is linearly proportional to the energy that's being absorbed by the material, and it's inversely proportional to the product of the mass and the specific heat capacity. And specific means per unit mass. And we're going to assume that this is constant with respect to temperature. That's not strictly true for most materials, but it's a good enough approximation to get us an approximate temperature rise to determine whether the brakes are going to be okay after this single use. Now, the Shigley book writes this as two separate equations. Its energy on the top and its mass on the bottom. I don't see a need for different symbols when they're expressed in different unit systems. You always need to keep your units consistent when you're working with equations. So just remember the concepts, and let's not think of this as two separate equations. So we're required to find how hot the brakes get after a single use, and that's just going to be the initial temperature that they started at plus the change in temperature. And the change in temperature is given by the energy dissipated divided by a material property, which is actually given to us, and mass, which is also given to us. Now remember, we've got four brakes. Each of them has a mass of 10 pounds, and so we'll take that into consideration. So let's figure out what is the energy, though. That's not given to us. But we do know that the truck has a speed of 100 feet per second, and we know what the relationship. We also know that the truck has a mass of 6,000 pounds. We know the relationship for kinetic energy, right? So E in this case is all kinetic energy initially, and that's 1/2 times the mass of the truck times its velocity squared. And in our case, that's 1/2. We've got a 6,000 pounds mass truck and a velocity of 100 feet per second squared. We're going to get 30 times 10 to the 6th. I guess that's feet squared per second squared. And also we've got a pounds mass factor in there. Now, this is a funny unit, pounds mass, foot squared per second squared. We have everything else. We're probably, it looks like, the bottom here, we're going to need to get this in terms of BTUs, right? Because it says that CP is 0.1 BTUs per pound mass degree Fahrenheit. That means the bottom is going to be, well, CP times M is that times mass. It says 10 pounds mass for each of the 4 breaks. So we've got a total of 40 pounds mass. And so on the bottom, we're going to have 4 BTUs per degree Fahrenheit. So that means for every 4 BTUs energy that we dissipate in the breaks, we're going to rise by 1 degree Fahrenheit. But we need to figure out what this is in terms of BTUs. So let's open up Google and see what it has to say. How much is 1 pound mass foot squared per second squared converted to BTUs? Let's see. Uh-oh, not finding, it's not doing its job here. It doesn't have that conversion factor. So let's think the units, the typical units of energy that we typically see in imperial units is pound force times a foot, right? It's a force times a distance. Pounds force times a foot. Let's see what that is. Okay, if we've got that, then we can probably figure out what we need. This is 0.001285. Okay, that'll help us. 1 pound force equals 0.00128507 BTUs. Now, what's a pound force in terms of pound mass and feet per second squared? Well, let's think about it in the other direction. I know that 1 pound mass times gravity, which is 32.17 feet per second squared, that's going to give me 1 pound of force, because we know that 1 pound of mass under the influence of gravity is going to produce 1 pound's force. So this gives us a conversion factor between pounds force and pounds mass. So we can replace the left side here with this here. And that means that 1 pound mass foot per second squared is equal to, let's divide both sides by 32.17. That's 0.000039946 BTUs. Okay, so 30 times 10 to the 6 of those is 1,198.38. Okay, now that we've got consistent units, we can find out what our temperature rise is. Our change in temperature is E over CPM, and that is 1,198.38 divided by 4, and this is in BTUs per degree Fahrenheit, and up top it's in terms of BTUs. So we're left with a temperature rise of around 300 degrees Fahrenheit. And that's the change in temperature. So our final temperature is our initial temperature plus our change in temperature. And that was 100 degrees Fahrenheit to start, plus our 300 change, and that's 400 degrees Fahrenheit. Now the second question was, is that okay? Yeah, after a single use, no problem. Most cars and trucks have brakes that'll work just fine up to about 700 degrees Fahrenheit, so we shouldn't have any problem.